once again, I have a couple of more neutralization reactions for you. These will go from a couple of different directions, just give you a couple of more ideas of how these problems can be approached. This one, instead of asking you for a volume, asks you for a molarity, but we're still going to approach it largely the same way that we did the previous problems. We're dealing with sulfuric acid and lithium hydroxide, so first let's go ahead and write the reaction. We're producing lithium sulfate and our expected water. So since I'm neutralizing my base here, I need to know just how much of this lithium hydroxide do I have floating around in that 500 mils. So here we go. 500 mils of my solution, but I don't want milliliters, those are no good. Off we go to liters. But I don't want liters, I want to know how many moles I have. So we have 3.5 molar solution per 1 liter. But we're only talking about hydroxide, not lithium hydroxide. So 1 mole of lithium hydroxide gives us 1 mole of that hydroxide ion. Multiply all the way across the top, divided by all the way across the bottom, tells us that we have 1.75 moles of hydroxide floating around in that solution that need to be nuked. Since I have 1.75 moles of OH, that means I need 1.75 moles of H+. Now the problem is I don't have H+ in a bottle. Oops. I have H2SO4 in a bottle. So first thing, let's get this to something I can actually take off the shelf. So if we look at our molecule here, per 1 mole of sulfuric acid, I get 2 moles of that, why did I write sulfate? Of that H+. Remember, it's our diprotic acid. We took off 1 H already. So I only need 0.875 moles of my sulfuric acid to get that 1.75 moles that I need to nuke my base. I need to have those 8.75 moles in a 250 milliliter volume. Well, I can't get molarity with milliliters. I gotta take it to liters. Molarity, if you remember, is moles per liter. Per liter. So I will need, look at that, a 3.5 molar solution of sulfuric acid. So that's just another approach that these, oops, you can't see that. That's just another approach that these problems can take, asking you for the molarity instead of the volume. Let's look at another one. This problem asks you for the pH of a solution that mixes an acid with a base. Oh, look at that. I used the same stuff. Ha! Totally accidental, I assure you. So I'm not necessarily neutralizing all of my H pluses and OHs in this problem. So I need to know how much H+, how much OH, what gets nuked. Woo, lots to take care of. But it is a reaction, so start simple. Anytime you have two things reacting, always start with your balanced equation. So my H pluses are coming from my sulfuric acid, my OHs are coming from my lithium hydroxide, but I need to know how much H plus and how much OH I have. It doesn't matter which one you start with, I'm going to go in the order of my problem. So first let's talk H pluses. I like to put a little indicator off to the side when I'm working these problems just to remind me what this big long stoichn looking thing is finding. That way if I get called away or a phone call, somebody comes in, distracts, whatever, I can go back to what I was doing. So we have 150 mils. I don't want mils, got to go to liters. I'm headed to moles. I want to know moles of H+. So I have a 2.5 molar solution. That gets me to moles. But I'm not interested in sulfuric acid. I'm only interested in H pluses. And I have 2 moles of my H pluses per every 1 mole of that sulfuric acid. So we multiply all the way across the top. We divide by all the way across the bottom, and we find out that we have 0.75 moles of H plus floating around. Hang on to that thought. Now let's figure out how much OH I have floating around in this solution. So this time we're going to do the same process, but we're going to start with the 350 mils of that solution. I forgot my smiley faces. It's my favorite part. Okay, we had a 1.5 molar solution per liter. This one's nice and easy because 1 mole of lithium hydroxide has 1 mole of hydroxide. So multiply across the top, divide by across the bottom, and we find out that we have 0.525 moles of hydroxide floating around in solution. Remember that in order to neutralize anything, I have to have 1 H and 1 OH. That makes our water here. So if we look at this, I'm going to have H plus left over. So if I subtract these two, I find out that I'm going to have 0.225 moles of H plus left over, because 0.525 moles of OH are going to go find 0.525 moles of H plus to hang out with, leaving this 0.225 moles of H plus just hanging around, still in solution. So my pH of this, if you remember how to calculate pH, all we need to do is take the negative log of this concentration. Technically, the formula is negative log of hydronium. But as we talked about before, these two are effectively the same thing. The water molecules in the solution are going to grab hold of this H plus immediately and turn it into this hydronium ion. So we're going to take this number and shove it in here. So negative log of, oh, I almost forgot. Look at that. Slight problem. These brackets, they stand for concentration. Woo! Glad I caught my mistake. You'll probably make the same mistake yourself at some point. I know I make them. This is moles. I need molarity. So we have 0.225 moles of our H plus floating around in 350 plus 150 milliliters. We want to divide it by liters. So I'm going to do my little cheat here. Let's see, 350 plus 150 divided by 1,000. Just make sure I do my math right. So that's 0.5. So 0.225 divided by 0.5 gives me 0.45 molar H plus. Ah, that looks much better. Can you see that? Yes. So this is the number that goes in my brackets. Woo! Glad I caught that mistake. So negative log 0.45 gives us a crazy low pH. But that should make sense because that is a crazy high concentration of H+. If you remember the other problems that we did. How many sig figs can I have? 2? No more than 3? All right, we'll have 3. So we have a crazy acidic solution. So this is just another type of problem that you might see in your doings of neutralization problems. Let's see if I can fit in one more before my time runs out. This problem effectively combines two concepts. It asks you to find the volume of your base needed to neutralize your acid, but it also asks you to find the concentrations of some leftover ions in that final solution. So let's jump right in. Here's our reaction. Forgive me for hurrying a little bit. I want to make sure I get this one on tape. Okay, hopefully by now you are familiar with our neutralization protocol, if you will. Since they gave me both the volume and the molarity of the phosphoric acid, I'm finding H plus first. 1,000 milliliters per liter. 1 liter per 9 moles of that solution. Oh my goodness. Since it's phosphoric acid, look at here. 1 phosphoric acid molecule gives me 3 moles of my H plus. So 350 times 9 times 3 divided by the bottom gives me a whopping 9.45 moles of H plus that I have floating around. Since I have this much floating around, I need this much OH minus to neutralize that. Off we go. If we look at our base here, 1 mole of hydroxide comes from 1 mole of your NaOH. Notice all my shortcuts here. I have a 6.8 molar solution. I'm going to go all the way to milliliters because I like the milliliters. Multiply all the way across the top, divided by all the way across the bottom. Tells us that we are going to need a lot of solution of our 9 molar phosphoric. Oh my goodness, that is a lot. Okay, so now let's talk about those concentrations of sodium and phosphate. I didn't make a solid here. Nothing changed as far as these two concentrations go. I'm not neutralizing them. I'm not making solids. So the concentration of sodium that I started with is the concentration of sodium and phosphate that I ended with. So all I need to do is go find where the ions started with. So let's start with the Na and just figure out how many moles of Na do I have divided by our total volume. Well, this was what we just found. So we have 1398.7 milliliters of your Na plus. Going back to liters, that was a 6.8 molar sodium hydroxide solution. But now I'm only caring, instead of about the OH, I'm only caring about the Na. So I find out that I have 9.45 moles of Na plus, but now we need to divide it by the total volume. Oh my goodness, I'm running out of time. So let's see, we had 1389.7 milliliters plus the 350 mils from our phosphoric acid. Gives me a total volume of 1.7397 liters equals a 5.43 molar Na plus. All right, let's see if I can do phosphate in record time. Phosphate came from our phosphoric acid. We had 350 mils of the phosphoric acid. We want liters. It was a 9 molar solution, but per 1 mole of my phosphoric acid, I had 1 mole of that phosphate. 350 times 9 divided by 1,000 gives me 3.15 moles of phosphate divided by that same total volume, since we mixed them together in the same beaker. Gives me a 1.81 molar solution of that phosphate. Can you see it? Oh, there it is. So that's just an additional thing that can be thrown in on these types of problems. I am out of time, so I will see you later.